Hello. This is a discussion of the use of ThreadMentor to do semaphores programming. It's rather simple, but I'd like to take this opportunity to talk a few uh, more things than just telling you how to use ThreadMentor for programming semaphores. So in ThreadMentor, there is a class called a semaphore, which has two methods, wait and the signal, just like the syntax we used in our previous lectures. So the class semaphore requires a non-negative integers and initial value. Some system may only require an integer, but in ThreadMentor, a non-negative integer would be needed. A name is optional. Why? You need a name for a semaphore. That's easy because in visualization, if you have several semaphores in your program, without giving a name, you would have difficulty to understand which signal is for which semaphore. So here's a simple example. Semaphore is a class. And here, SEM is defined to be a semaphore. The first argument is a string, which is assigned to the name of the semaphore SEM. And it is, of course, optional. The second argument is an integer, non-negative integer, the initial value of the semaphore. So when you do semaphore.wait, it means you execute the wait method of semaphore. And the signal call is just like this. So if the initial value is 1, then this is a mutual exclusion for this example. So your critical section is between this wait and this signal. Now, if you declare semaphore as a pointer, then in this case, just like we create a class by the use of the new keyword. So exactly the same, except that we declare sem as a semaphore, and then we create it with a string and a non-negative initial value. Then the call to wait and the signal has to be changed to reference. So that is this simple. So here's an example for the 4 chairs version of semaphore. So here we declare a semaphore called chairs with initial value 4. We declare an array of mutex. Mutex is just a semaphore to be used as a lock and unlock. Of course, you could also declare the 5 chopsticks initialized to 1 to be a array of semaphores. But as we discussed somewhere, the mutex is easier to use because if a process successively locks a mutex, only the owner, and that process will become the owner of this mutex. Only the owner of a mutex can execute an unlock. So except for replacing the keyword or the type semaphore by a mutex, it's all the same. We have initial value here. So here is the philosopher class. It has an initial or a constructor for initialized number of n, which is the number assigned to that philosopher and the number of iterations for that philosopher to eat, think. And it has 3 items in the private section. Number is the number of its left neighbor and how many iterations for that philosopher to do the thinking, eating cycle. And again, a thread function. Here is the semaphore function thread func. So we have initial value left to be initialized by the number. And the right neighbor is number plus 1 mod 5. So initialize the function, and then we iterate this number of times. For each iteration, a philosopher acquires a chair. Now, because we only allow 4 philosophers to sit down, therefore the initial value here is 4. And then acquires the left chopsticks. Here, if we declare it as a mutex, instead of using wait, you should use luck. So if this philosopher I successfully locks this mutex, philosopher I becomes the owner of this mutex. And then philosopher I locks the second mutex for its right neighbor. If it's successful, he could eat. After eating, release both chopsticks. The order of this unlock actually doesn't matter. And finally, release the chair. So look here, chops are defined to be 5 mutexes. So when you wait on a mutex, you execute a lock. When you are done, you execute a unlock. So this is the only difference. So the syntax of a semaphore under ThreadMentor is exactly the same as in our previous lectures. Now, let's take a look at a very interesting but very simple problem. We call it the smoker's problem. We need 3 ingredients to make a cigarette: tobacco, paper, and the matches. Now, an agent has an infinite supply of all 3. And we also have 3 smokers, but each smoker has only an infinite supply of 1 ingredient. In other words, smoker 1 has tobacco, smoker 2 has paper, smoker 3 has matches. Each of the smoker would need the other 2 ingredients to make a cigarette and smoke. So all 3 smokers and the agent share the table. So the logic goes as follows. The agent puts 2 ingredients on the table and tells the smokers who needs these 2 ingredients. This smokers got these 2 ingredients, clears the table, then make a cigarette. So this is a very simple problem, isn't it? But the original problem of this smoker's problem or cigarette smoker's problem is rather not so obvious. So this is what we said. The agent at 2 randomly selected different ingredients on the table and it notifies the needed smoker. A smoker waits until the agent's notification, then takes the 2 needed ingredients, makes a cigarette, and smokes for a while. So this process continues forever. How can we use semaphores to solve this problem? I'm sure many of you would be able to solve this problem in just minutes because this problem is so simple. So please pause for a while and think about how will you be able to solve it. So here's a diagram for a possible solution. the agent put 2 ingredients on the table and notifies the smoker who needs these 2 ingredients. This is notification. And then wait for the table to be cleared by the smoker who needs the 2 ingredients. Once the table is cleared, the agent is able to put 2 more ingredients on the table and tells the smoker who needs this ingredient. Wait for the table to be cleared. On the other hand, for a smoker, it waits for the ingredients. As we mentioned, the ingredient will put the ingredients are generated by the agent and put on the table and notified the smoker. So the smoker wait for the ingredient to become available and take the ingredients, clear the table. Clear the table means this smoker signals the agent so that the agent would know, okay, the 2 ingredients on the table are taken. So the agent could generate the next one. For the smoker, because the ingredients are taken, so that this smoker could just make a cigarette and smoke for a while and comes back for the next round. So isn't it very easy? I'm sure everybody would think this is a very easy problem. And this version is a rather simplified version, as we will see later on. So let's say we name smoker 0, smoker 1, and smoker 2. And smoker 0 has 0, ingredient 0. Smoker 1 has ingredient 1. Smoker 2 has ingredient 2. So for smoker 0, it has 0 and needs 1 and 2. So we define the semaphore 0 for the needed ingredients 1 and 2. For smoker 1, it has 1 and it needs ingredients 2 and 0. For 2 and 0, we assign a semaphore 1 for that. Smoker 2 has ingredients 2 and needs 0 and 1. So for 0 and 1, we use semaphore 2. So once you get to this point, the remaining is pretty easy. Now, for the class A, the agent, and SMK for the smoker. I don't have enough space to put everything on a single slide, so I use abbreviations. So for the agent, it has nothing. It's just a thread function. For the smoker, it needs a number, the name, smoker 0, smoker 1, and smoker 2. So it has a constructor receiving the assigned number. And again, there's a function, and this assigned number would be used to initialize a private integer, which indicates the assigned number, which is done here. This is the argument used in the constructor. And the constructor makes the assigned number to the private number. So for smoker, initialize the thread function and loops forever. For each iteration, it waits for the notification from the agent. And this semaphore number represents the 2 needed ingredients. After this smoker is notified, it clears the table. So it signals the table semaphore and then smoke for a while. So this is a smoker part. Now, let's take a look at the agent. Again, the agent has a thread function and a random number representing which 2 ingredients is. So we generate a random number in the range 0, 1, or 2. So 0 means ingredients 1, ingredients 2, and so on. So once this random number is generated, the agent signals the corresponding semaphore and weight. Once the table is cleared by the corresponding smoker, the agent runs for the next iteration. So this is the main program. We have an agent class A. We declare smokers as an array of 3 pointers, each of which points to a smoker thread. So first of all, we generate the agent. It's already there. Therefore, we simply execute the begin method to run the agent. Then we iterate 3 times. So for each time when I is 0, we create a new smoker, assigning the value I. And then we run that smoker's begin method and keep running. And then we executed agent.join. That is the main program waiting for the agent to complete. Then we did some discussion here. Even though the agent and all 3 smokers iterates forever, we still need a join here. Why? Hope you understand it. Think for a while before you hear my explanation. So if we remove this line, that is, there's no join here. The reason you may have some doubt is that the agent here never ends. Then this join call does not seem to be needed. But if you don't have this join here, after creating the agent and the 3 smokers, the main program exits. Once the main program exits, everything created by the main program will be gone. In other words, the agent and the 3 smoker thread will be gone. Is that what you want? Definitely not. Therefore, we must have this join call here, even though this join call does nothing but blocking the main program so that the main program will not exit. So once you know this, this semaphore in the mutex, in your C++ exercise, you don't need to use sprintf followed by write, so that every line will be printed out completely by a thread. How do you do that? Either you declare the mutex, say screen lock, or a semaphore screen lock with initial value 1. So you still print the whole line to a string. That string is definitely local to that thread. So before you print the whole thing out, what would you do? You simply screen lock.lock or screen lock.wait. After printing, you screen lock.signal or screen lock.unlock. That is much easier. Now, if you want to print it out a line item by item, then every item you want to print it out could be, even though you locked the screen. Say in thread A, you want to print the value of X. In thread B, you want to print the value of Y. Now, when you print X, you may screen lock.lock, print X, see out X, and then screen unlock. Then you do not have any guarantee that the value of Y could be mixed with the value of x. So the value of x and the value of y could appear on the same line. So I still strongly recommend you print everything to the same line, a string, and then lock screen and print the whole thing out. In that way, you avoid the use of system call write. But of course, that is your choice. Then we spend some time to talk about the general smoker's problem. As I mentioned earlier, the simplified smoker version was discussed in previous slides. And the original or the general smoker's problem was studied by Suhas Patil in 1971. The agent and smokers have code something like this. We still have a table with initial value 1. And we have 3 semaphores with 0, 0, 0. But this time, each semaphore only represents 1 ingredient. That is semaphore 0 corresponding to ingredient 0. Semaphore 1 corresponding to ingredient 1, and so on. Rather than 1 semaphore represents 2 ingredients. So in this case, the agent will do the following. The agent generates 2 ingredients, I and J. And the agent wait table to be cleared, and then signals the semaphore corresponding to ingredient I, and then signal the semaphore corresponding to ingredient J. So the agent signals each ingredient semaphore rather than 1 semaphore corresponding to 2 ingredients. Now let's take a look at the smokers. And smoker who need M, ingredient M, and ingredient N, it would look like this. Wait for ingredient M, wait for ingredient N. And then after both ingredients are available, this smoker signal the table semaphore to clear that and then smoke for a while and loops back. Now, please go through the simple code several times to make sure you understand the use of semaphore. Now, each semaphore elements corresponding to exactly 1 ingredient, rather than each semaphore corresponding to 2 ingredients as we discussed earlier. So please do not continue before you understand the code. Now, if you reach here, you probably have figured it out. There could be a deadlock. That's right. Please use an execution sequence to reveal a possible deadlock. Actually, the original paper published by Patil used this example to illustrate this general version of cigarette smokers indeed would have deadlock. However, he made a incorrect claim, saying that the semaphore we discussed so far may not be able to solve this problem. Solving this general smoker's problem with the semaphores discussed here is a bit tedious, but doable. The first such solution was published by David Parnas, a very well-known software engineer, researcher, and practitioner. He published a solution This solution doesn't have deadlock, but he did not prove it. And later on, Nico Habermann proved that Parnas' solution was correct. Now, both Patil and Dijkstra proposed the so-called parallel weight approach to solve certain problem. For example, in Dijkstra's paper, he proposed parallel weight in order to solve the Dining Philosophers problem. And Patil proposed parallel weight to solve the general smokers problem. I put the citation here. Hopefully, if you're interested, you are able to request a copy from Interlibrary Loan. And when you have free time, read it. So what Dijkstra proposed was to extend the weight and signal calls so that each weight and each signal could take multiple semaphores. So instead of keep using weight, I use weight P. P means parallel. So weight P, S1, S2, Sn, these Si's, some are semaphores. So a process calls weight P does not wait if and only if every semaphore listed as argument has a positive counter value. That's Si with a counter value greater than 0, S2 has a counter value greater than 0, and so on. Only if every semaphore counters is positive, the caller to weight P does not have to wait. Of course, every semaphore counter would be decreased by 1. For signal, we use signal P to indicate parallel signal. It's simple. We just add 1 to each semaphore. Of course, once you add 1 to each semaphore, the counter of this semaphore could change. One of the processes waiting for all of this semaphore it waits upon will become positive. The implementation is a bit more complex, but let me stop here because we'll talk about later on. Of course, without digging into too much. So Dijkstra called this type of weight and signals a parallel weight, but he still used sequential signal. Suppose you are going to do this, is signal P S1, signal P S2, and so on. Now, a general form of semaphores called semaphore array was proposed by Tilak Agerwala in 1977. It does not mean between 1971, when parallel weight was proposed, to 1977, semaphore array was proposed. There were nothing new, wrong. Whole lot of a proposal to generalize Dijkstra semaphore was proposed. But Agerwala's probably was the most popular form. So here we introduce two sets of semaphore, S1, S2, Sn, T1 underbar, T2 underbar to Tm underbars. So we have two sets of semaphores. Now we use weight E here. E means extended. Weight E and the signal E are defined as follows. When a process calls weight E with these two sets of semaphores, what weight E is going to do is, if every semaphore in the S set has counter greater than 0. And all semaphore in a T set has semaphore counter 0. In that case, every semaphore in the S set would have this their counter reduced by 1 in return. So in otherwise, if one of these conditions fails, then the caller to this wait E blocks. So quickly go through it. A wait E call would take 2 sets of semaphore, S set and the T set. If a process calls wait E, this process does not wait if and only if the counters of all semaphores in the S set is greater than 0. And the counter of every semaphore in the T set is 0. In that case, the counter in the S set would be reduced by 1, returns. Otherwise, if one semaphore here has its counter equal to 0 or less than 0, or if a semaphore in this T set here has its counter not equal to 0, then the caller would be blocked. Now the signal call is pretty simple. Notice here, S1, S2 are placeholders indicating it's a semaphore, not a semaphore set for waiting for 0. Okay, so because in this case, we do not consider whether a semaphore would have this counter to become 0. So you just provide a set of semaphore here. When a process calls signal E, every semaphore counter will be at 1 to it. There's no blocking. So let me quickly go through it. When a process called wait E, it does not have to wait if and only if all counters in the S set is greater than 0 and all counters in the T set are equal to 0. In this case, the S set counter will be reduced by 1 and the caller returns. If this condition fails, in other words, if one counter is in the S set is not positive, or a counter in the T set is not equal to 0, the caller is blocked. And then for the signal part, we just add 1 to the counter to every semaphore listed in the argument. A note, counters of semaphore S1 to Sn are tested and decreased at the same time. At the same time, all counters in the T sets are tested for 0 at the same time. In other words, the execution of wait S, wait E, and signal E are atomic. So when a call to wait E is being executed here, no other process will be successfully executing wait E and so on, just like what we talk about, the wait call and signal calls. Now, one more thing, it's just a notational notes. Each of the semaphore in the T set, Ti, is a typical semaphore. We just use an underbar to indicate that semaphore at Tj is a semaphore for testing for 0. This semaphore is not for testing its counter for greater than 0. So actually, we have 2 sets of semaphore here. One set for decrement, the other for testing. We use a notation to indicate. The T set is for zero testing. Hope you understand that and don't get confused. Now, with this kind of a extend semaphore, how powerful is it? Okay, so if we do not use the T set, our Agerwala's extension is just like a Dijkstra's parallel weight. So we remove the T set. So when we call weight E, the caller will not wait if and only if all counters in the S set are greater than 0. And their values are reduced by 1 in returns. And if there is one semaphore in the S set, its counter is not greater than 0, the caller is blocked. By the same reason, because the signal part does not have the T set, because it does not distinguish the S set and the T set, so we just add 1 to the counter. So this is the form that does not use the T set. Now, if the S set semaphore are not used, this extension becomes waiting for all the counters in the T set to become 0. This is the form. So when a process calls wait E with the T set, then if every counter of the semaphore in the T set is 0, so it returns. Because there's no S set, no semaphore counter decrements there. And if one of the T set semaphore is non-zero, so the caller is blocked. It's very simple. Now, with this extension, the philosopher's problem can be solved very easily and very naturally. Let's take a look at philosopher. We declare 5 semaphores. So it was initial value 1. So for philosopher I, thinks for a while. When philosopher I wants to eat, it calls wait E, wait for his left chopsticks and the right chopsticks. Only if the counter of his left chopsticks and the counter of his right chopsticks are both greater than 0, which means his left neighbor, his right neighbor is not eating. This call to wait E would return. And then philosopher I can eat. After eating, philosopher I calls signal E to release the left chopsticks and the right chopsticks. So isn't it this solution is more intuitive than the version discussed in the Dining Philosopher lecture? Yes, of course. And actually, this solution was proposed by Dijkstra. But for some reason, Dijkstra rejected this parallel weight. Instead, he continued to use his own signal and weight in his very well-known early operating system called the THE. You probably will learn something of this THE system in an operating system course. So let's study the general smoker problem. Here is the agent. So the agent waits for the table and generate 2 ingredient I and J, signals ingredient I and ingredient J, and loops back waiting for the table. Now, for the smoker K, who needs ingredients N and N. So it waits for ingredient M and ingredient N at the same time. So smoker K can continue only if the counter of ingredient M and the ingredient N are positive. If one of them is not positive, smoker K is blocked. So after taking the ingredient, smoker K signals table to clear the table so that the agent could put the next two ingredients there. So isn't it with this parallel wait help us to write our program in a more intuitive way? I'm sure if you understand this, you will agree. But the question is, we only use the S set here. We did not use the T set. The T set semaphores are denoted with a underbar. Sorry, I should use overbar, but in PowerPoint to generate overbar is rather troublesome. So I use underbar. So let me show you a very simple example to illustrate the use of underbar. As we mentioned, how do we use the T-set semaphore that's underbar? Here's a very simple example. This example is not only simple, but important in operating system, and probably also important in your career. If in your career you have to write program to allocate resources. So let's say we have a set of processes, PI. PI has higher priority than its next one, PI plus 1. So suppose we have a set of process here. So process P1 has the highest priority, followed by P2, followed by P3, and so on. So PI has a priority lower than PI minus 1, but has a higher priority than process P plus 1. So process has assigned priority. Remember, when we talk about process control block, the PCB, in which one of the item is process scheduling priority, right? So that priority can be used for resource allocation as well. So how do we use this priority to perform resource application? Here it is. The processes request access to the resource. Suppose we have only one resource. The processes request access to the resource and are allocated in a mutually exclusive way based on the priority. Of course, most system resources must be used in a mutually exclusive way. But what does that mean by priority? It means a request by a process is not honored until all higher priority requests are taken care of. For example, suppose PI requests to use a resource. PI won't get this resource until P0, P1, P2, P3, up to PI minus 1 finish using this resource. That is until no process that have higher priority than PI is using that resource, then PI can use it. And if a process with a higher priority than PI, then that process would have that resource allocated than PI. So this is the key. Now, if you think this, used with the traditional semaphore, this program is going to be a bit difficult to write. You could think about it. Now, suppose we are able to use S set and T set. The program is rather short. So here, let me remind you, S1, S2, up to all the S semaphores are typical semaphores. When we put a underbar under a semaphore name, it means that semaphore is going to be used for zero testing, okay? So look at how process I, that's PI, would get this resource. We declare a semaphore array, Sm, to control n process initialize or 0. And we have a semaphore R, which is to be used as a mutex for mutual exclusion. So process I loops. So process I calls signal I, passing it with semaphore Si. Notice here, this is S set. So definitely, as a counter of Si will be increased by 1. This signal means process I makes a request. After making a request, process I must wait for the resource to become available. So process I calls wait E with one single semaphore R in the S set. All semaphores S1, S2 to Si minus 1 would be in the S set, would be in the T set. That is, when process I calls wait E with this semaphore, it does not have to wait if R has a counter greater than 0. And the OR counter in this set are 0. So after it, if S1 is 0, S2 is 0, Si minus 1 is 0. What does that mean? It means none of these processes, process 1, process 2, up to process I minus 1, made a request here. So this is a tricky part. We call signal E with semaphore Si, meaning I make a request at 1 by adding 1 to it. So now semaphore S1 to Si minus 1 are used as the T set semaphore, testing for 0. Now, if none of these semaphore counter is 1, then that means all higher priority processes are not requesting to use the semaphore. Therefore, process I continues. After process I continues, process I calls wait E to its own semaphore. What does that mean? It means I withdraw my request. So the counter of Si returns to 0. So look here, the process I still has a mutually exclusive use to the resource because of this R semaphore. The R semaphore was initialized to 1. If process I can pass through this wait E, the counter of R is 0. All subsequent call to wait E will be blocked because the R semaphore is used in the S set. So after using the resource, the process simply signal E to release R and returns back. So the key concept here is process I use signal Si to make a request, making its counter non-zero. If its counter is non-zero, it will block the request by Pi plus 1, Pi plus 2. Then Pi waits for the counter of R, the mutual exclusion mutex to become greater than 0, and all counters of the processes whose priorities are higher than pi to become 0. A counter becomes 0 means that process has already withdrawn its request. Then process I continue withdrawn its request, use the resource, release the resource. Now look at this solution. Isn't it very easy to write? If you use parallel wait and parallel signal. So you may want to say, nearly all systems only provide a traditional Dijkstra wait and signal. So why are you bothering talking about this? Well, I do have a good reason. That is in Unix. Unix system 5, starting with Unix system 5, the semaphore capability started to appear. But unfortunately, the semaphore implemented in Unix and currently Linux is not what we are used to. That is, the semaphore implemented in Unix and Linux is not wait in the signal. The implementation in Unix and Linux is the so-called semaphore arrays, very much like Agerwala's semaphore extension. Now you know why I spent 12 slides to talk about this until we get the Agerwala's semaphore extension done. So just like when we talk about shared memory, we call semaphore get to obtain a semaphore set using a key. Now, in Unix, there is no wait E, there's no signal E. Instead, Unix uses a single system called semaphore operation, SEMOP, to integrate everything you can do with Agerwala's semaphore extension into one call. As you can imagine, in Unix, the use of semaphore operation is rather complex. Because we're not talking about a Unix system here, so I leave this for you to dig into Unix and the Linux manuals. So a semaphore OP call allows you to pass some argument to operate on a semaphore set. For each element in a semaphore set, you could do the following. You simplify plus, you don't perform any operation on that semaphore elements. Or you could pass a value. This value can be added or subtracted from to the semaphore counter. Or a 0 means you force that semaphore elements to wait for that semaphore element to become 0. So now if you ignore this, you can add a value or add a value to or subtract a value from the semaphore counter. So in this case, wait and signal are there. Not only you add 1 or subtract 1, you could use an arbitrary value. And then if you want to wait for the semaphore counter to become 0, you could set a 0 there, indicating you want to force that semaphore, the caller to wait until the semaphore to become 0. So I don't want to go into too much detail because it's too complex to be discussed. But anyway, this 13 slides at least help building you up step by step until we get this unique semaphore discussion. Now, before we leave, let me introduce to you another solution to the dining philosopher problem, also suggested by Dijkstra in his paper. This is the citation. So many textbooks credit this solution to Tenenbaum, Andrew Tenenbaum. That is wrong. Maybe Tenenbaum rewrote this solution using the concept of monitors, but it's just a rewrote rather than discovered or proposed by Tenenbaum. We will talk about this when we reach the monitor discussion. So here we have some global items. We have a mutex initialized to 1. We have 5 semaphores. This semaphore is not for blocking chopsticks. Instead, it's for blocking some philosophers. So the name is to eat. Initially, no philosophers is allowed to eat. Then we introduce an integer array of 5 elements, a state. Initially, it's all thinking. That is, a philosopher, when he is thinking, his state is set to thinking. When this philosopher wants to eat, before he can eat, his state would be hungry. After this philosopher successfully acquires both chopsticks, then this philosopher's state is changed to eating. So we use a function called can eat to determine whether a philosopher can eat or not. So the argument I is a philosopher number. So when philosopher I can eat, well, the condition is so simple. Philosopher I can eat if and only if his left neighbor and his right neighbor are not eating. His left neighbor is not eating, so his left chopsticks, which is the right chopsticks of his left neighbor, is free. If philosopher I's right neighbor is not eating, so philosopher I's right chopstick is available. So this function can eat simply goes as follows. It takes a philosopher number. If his left neighbor is not eating, his right neighbor is not eating, but philosopher I is hungry, then philosopher I can eat. Therefore, inside this can eat function, it calls, we don't know which philosopher calls can eat, okay? So we can just say inside this function can eat if it finds out philosopher I can eat. So the caller of this can eat function signals philosopher I's semaphore to eat, allowing philosopher I to eat. That is adding 1 to the counter of philosopher I's to eat function. So this is pretty easy. Now, how do we write a philosopher? Of course, the array state is shared by all philosophers. When philosopher I is hungry, philosopher I must set its state I to hungry. To do so, philosopher I must lock the array state, then set hungry to his own state, and then check to see whether he can eat. If he can eat, then his to eat semaphore would be signaled inside the function can eat. So anyway, this philosopher I won't be blocked in can eat function. So philosopher I returns, release the semaphore, and then wait on to eat semaphore. If previously philosopher I can eat, philosopher I has already signaled itself. Therefore, to eat counter is 1. On the other hand, if philosopher I through calling can eat function, he cannot eat. So that signal call would be bypassed. As a result, the counter of to eat is still 0. So philosopher I would be blocked here until someone signal this to eat semaphore. If someone signals this to eat semaphore for philosopher I can eat. Therefore, philosopher I changed its state to eating and start to eat. After eating, philosopher I locks the state array and start thinking. Before it goes away, he must put down the 2 chopsticks he acquired. So what he has to do is he calls can eat with his left neighbor. I plus 4 mod 5 is left neighbor. So philosopher I calls can eat with his left neighbor's ID. If his left neighbor can eat, so philosopher I inside can eat would call his left neighbors to eat semaphore. And then calls can eat with his right neighbor's ID. If this right neighbor can eat, then his right neighbors to eat semaphore will be increased by 1. So after that, philosopher I simply released the mutex. So in this solution, a philosopher can eat if and only if he could acquire both his left chopsticks and his right chopsticks. So this offers you a different solution than the one you have learned previously. In all previous solutions, except for the Dijkstra parallel weight solution, chopsticks are acquired 1 by 1. But in this Dijkstra solution, we are no more looking at chopsticks as something to be protected. Instead, we block the philosopher until that philosopher could get both chopsticks. So this is the last slide in our lengthy discussion of semaphore. And I hope you really like it. In the next lecture, which is longer one, we will discuss how to catch race condition in a program using semaphores. This is not an easy work, and there is no algorithm that can help us to do it. We'll explain there. So let me stop here and see you in my next lecture talking about race condition revisited. Goodbye.